Good day, everyone. Welcome to our educational video. Please ready yourself to learn because in this video, we are about to tackle the coordinate systems and positioning methods.
Today we're going to discuss the importance of the reference coordinate systems. So when we say the reference coordinate systems, it ensures that all the spatial data is aligned correctly. So the reference coordinate systems, it allows the global and local data integration, meaning it unifies the first geographic information system, or what we call the GIS. Just like, for example, the WGS 84 that serves as a global standard for uniform spatial data. So we also have the local datums that is used in specific regions, specific countries. Here in the Philippines, we use PRS 92 that offers a regional precision.
Next is defining coordinate systems and their types. What is a coordinate system, by the way? Well, it is a framework for precise location measurement on Earth or in space. It uses one or more numbers or coordinates to uniquely determine position. Next is let us identify the common types used in geodesy, which is the geographic, projected, and Cartesian. For the geographic, it directly locates points on Earth's curved surface. It uses angular units, latitudes, and longitude degrees. Based on spheroid or ellipsoid, and for example of this is the WGS 84. Next is the projected. It is a 2D representation on a flat plane, or for example of this is a map, a projected map. This transforms 3D GCS data via map projections, as what I've said lately. It minimizes distortion for specific regions. This uses linear units such as meters or feet. For example of this is the UTM, or the Universal Traverse Mercator. Next is the Cartesian, or the XYZ. It is a rectangular 3D coordinate system that it defines points relative to a fixed origin, or the 0, 0, 0.
We're examining the crucial reference frames that establish spatial foundations for high precision location both globally and right here in the Philippines. These frameworks are essential for accurately defining where we are on Earth. The core global standard is the World Geodetic System 1984, or WGS 84. WGS 84 is the Earth-centered Earth-fixed system that serves as the universal data for global positioning, most notably used by the Global Positioning System, or GPS. Its widespread adoption makes it the standard for global navigation and cartography. Locally, for all surveying and mapping activities, the Philippines mandates the use of the Philippine Reference System of 1992, or PRS 92, established via GPS campaigns across 330 stations. PRS 92 provides a single unified system to govern all land administration, ensuring a particular space on the ground has only one official location in any Philippine map. This helps resolve boundary overlaps and gaps.
So now we're going to define the geoid and the ellipsoid. So for information like everyone, the geoid and the ellipsoid is an Earth's model. So when we say the geoid, it represents the Earth's true gravity-based surface. As we can see on the representation that is included in the slide, it has an irregular surface. So it is used as a vertical reference for accurate height and elevation measurement. So that is the use of the geoid in the surveying. So the ellipsoid naman, an ellipsoid, as we can see on the representation, it has a smooth surface, but it is used for mathematical model that approximates the Earth's shape. It is used for horizontal coordinates and GPS positioning because it simplifies the calculation.
Next is the relationship between geoid, ellipsoid, and topographic surface. As we all know that a topographic surface is the physical Earth itself. Geoid is the mean sea level of equivalent. Next is the ellipsoid, which is the mathematical reference or the mathematical representation of the Earth. Above geoid is we have the orthometric height, and above the ellipsoid is the ellipsoidal height. We also have the geoid undulation or the geoid to ellipsoid separation. Orthometric height is the height above the geoid at what I've said earlier, commonly known as the elevation. It is the practical or real world height. While the ellipsoidal height is the height above the ellipsoid, of course, it is directly obtained from the GPS or the GNSS. It is the geometric satellite derived height.
Our mapping systems rely on accurate positioning, but they often use diverse standards. This is why we need coordinate transformation, which is the process of changing a point's coordinates from one system to another. It is the key to bridging diverse geographic systems for precision. To understand the transformation, we must recognize its two main components. Datum. This is the definition of Earth's location reference. A datum uniquely defines all locations on Earth with coordinates. We've previously discussed examples like WGS 84 and PRS 92. Projection. This is the mathematical process that transforms 3D coordinates onto a 2D flat surface for mapping. Common examples include the Universal Transverse Mercator or UTM and the Lambert conformal conic projections.
So now we're gonna discuss the problems with different coordinate system or iba-iba nga coordinate system. So in this, using multiple coordinate system can lead to spatial data misalignment and positional errors. Difference in datums on Earth's models, the geoid or the ellipsoid, can cause elevation discrepancy and inaccurate measurements. These issues are solved through coordinate transformation, which ensures the data compatibility and the global precision for systems like the GNSS and the RTK. Or again, the GNSS is a global navigation satellite system, and the RTK is the real-time kinematic.
Have you ever wondered if what is the difference between the point positioning, relative positioning, and kinematic positioning in GNSS? Surveying? Well, in this video, we are going to discuss it all. First, for the point positioning is it has a single receiver operation, low accuracy in meters, and no base station needed. This is for basic navigation and mapping. While the relative positioning, this requires two or more receivers, higher accuracy 4 cm to sub-meter. It has correct errors via base station data. This has the precise surveying and agriculture. Next is for the kinematic positioning. Well, it has a continuous high accuracy data. It utilizes relative techniques. For example, is the RTK. It is ideal for dynamic applications and it is autonomous vehicles, autonomous vehicles rather, or the drone mapping.
When we talk about location, there are two fundamental ways to define a point on Earth. First, geographic coordinates and Cartesian coordinates. Understanding the difference is key to precise mapping. Geographic coordinates use latitude and longitude to define points on Earth's curved surface using angles relative to the equator and the prime meridian. They are often based on a reference ellipsoid. The advantages are clear: they offer global coverage and a universal reference, making them initiative for expressing locations globally and directly relating to the Earth's spherical nature. Cartesian coordinates define points in a 3D rectilinear space using linear units like x, y, and z axes, usually in meters or feet. This can be geocentric or projected. The main advantage are they use uniform units for accurate measurements, allowing for simplified mathematical calculations for distance and area, making them ideal for local, precise engineering and surveying.
So for the last discussion, we're going to discuss about the real-world application of the geodesy. So in mapping and GIS, it provides the foundation for accurate maps and spatial databases that supports urban planning and resource management. In cadastral surveying and land management, it defines the legal property boundaries and supports the land registration and taxation system. So in the understanding the Earth's complex shape, which is the geoid and the ellipsoids, is simply defined as the geoid shows the Earth's true shape based on the gravity or for the height, while the ellipsoid naman, it has a smooth model for position and mapping. It is used for the coordinates. That's all for the presentation. Thank you so much.